The topic for today is magnetic effect of current. Magnetic effect of current. We all know when an electric current flows through a conductor, it produces a magnetic field. The direction of this magnetic field can be found using right hand thumb rule. That is, if you hold the thumb in the direction of the current, then the tips of the finger encircling the conductor will give the direction of magnetic lines of force. Biot-Savart law. The strength dB of a magnetic field due to a small current element dl, which carries a current I at a point P, which is at a distance r, is directly proportional to the current flowing dl sine theta and inversely proportional to r square. Therefore, magnetic field dB is given by mu naught by 4 pi I dl sine theta by r square. Magnetic field due to a straight wire carrying current. So since this derivation is not required for the exam, I'm just giving you the formulae to calculate it. So the respective angles are given in the diagram for your information. B is equal to mu naught by 4 pi I into sine theta 1 plus sine theta 2. If the straight wire is infinitely long, then theta 1 and theta 2 becomes equal to 90 degrees. Therefore, magnetic field is given by mu naught I by 2 pi A. Magnetic field due to a circular loop carrying current. Since this derivation is required, I'm doing it in a bit more detail here. So consider a circular loop which is having a radius equal to A, and we want to find magnetic field at a distance x from its axial point at a point P. So magnetic field is given by mu naught by 4 pi I dl sine theta by r square. Since theta is between dl and r, and that's equal to 90 degrees, therefore magnetic field is given by mu naught I dl by 4 pi into r square. So the magnetic field at this point by right hand thumb rule can be found to be in this direction due to that current element dl. Due to a current element here, the magnetic field is found to be dB in this direction. So due to the diametrically opposite current element, dl dB cos pi gets cancelled when we resolve both the dBs into their respective components. So the total magnetic field B will be equal to integral dB sine phi, and sine phi is equal to A divided by R, which is root of A square plus X square the whole square. So substituting the value of sine phi, we get B is equal to mu naught I A square by 2 into A square plus X square to the power of 3 by 2. So please feel free to pause the video and do this derivation. Now, at the center O, if we want to find the magnetic field, the distance x for that is equal to 0. Therefore, we get B is as mu naught I by 2A. If the point is very far away from the coil, then A is very much lesser than x. So you can neglect your A here. So B becomes equal to mu naught I A square divided by 2x cube. Ampere's circuital law. Ampere's circuital law gives a relationship between current and the magnetic field produced by a current carrying conductor. So it states that the line integral of the magnetic field along an imaginary closed path called as Amperian loop is equal to the product of permeability of the medium and the current enclosed by that path. Magnetic field due to the current carrying wire of infinite length using Ampere's law. For this, we consider an Amperian loop of radius r if we want to find a magnetic field at the point A, which is at a distance of r from the conductor. So integral B dot dl is equal to mu naught into I, or B into integral of dl from 0 to 2 pi r is mu naught into I, because magnetic field along that circular path is a constant, as it is all points are equidistant from the conductor. So B into 2 pi r is mu naught into I, or B is equal to mu naught I by 2 pi r. Magnetic field due to a thick current carrying wire using Ampere's law. Outside the wire, the calculations remain similar to what we saw previously. Therefore, B is mu naught into I naught by 2 pi r if I naught is the current flowing through that thick conductor. On the surface, R becomes equal to A, the radius of the cylinder. Therefore, B becomes the constant, which is mu naught I naught divided by 2 pi into R. Inside the wire, not all the current I naught is threading through a path of radius, let's say small r. So we need to find the current enclosed by that path. So that will be equal to r square by a square into I naught, because the current flowing through a cross section is proportional to the area of that cross section. So B into 2 pi r is equal to mu naught into r square by a square into I naught. Hence, we get the magnetic field. So the diagram alongside here shows the variation of the magnetic field with the distance r. If the distance is lesser than the radius, that is inside the conductor, magnetic field is directly proportional to r. On the surface, it has a constant value, and outside the wire, it is directly proportional to 1 by r, or you can say inversely proportional to r. Magnetic field due to a solenoid using Ampere's circuital law. Now, for finding the magnetic field outside the solenoid, we consider a path A, B, C, D. Here, the net current enclosed by this path is 0, because the current that enters the current that enters the solenoid here leaves the solenoid over there. So the net magnetic field will be equal to 0. Now, inside the solenoid, for that you consider a path PQRS. Line integral of B dot dl will be the line integral of B dot dl over each one of these paths. For PS and RQ, B and dl are mutually perpendicular. Therefore, the magnetic field there is 0. Also, since SR is outside the magnetic field, outside the solenoid, there also the magnetic field is 0. So the only contribution is from this region PQ. Hence, by Ampere's circuital law, B into L, which is the length of PQ, should be equal to mu naught into, if N is the capital N is the number of turns, then it is mu naught into capital N into I. Let small n be the number of turns per unit length, then we can replace our capital N as small n into L. So we get B as equal to mu naught small n into I. Magnetic field due to a toroid using Ampere's law. On the surface of the toroid, your magnetic field is given by mu naught into Ni, similar to what we saw on a solenoid. Inside the toroid, there is no current enclosed in this region. There is no current enclosed, so the magnetic field there will be 0. Now, outside the toroid also, there is no since it is outside that solenoid or the toroid, the current coming out of the plane of the paper is cancelled by the current that goes into it. Therefore, the magnetic field outside the toroid is also equal to 0. Now let's solve two questions. A long straight wire carrying a current of 30 ampere is placed in an external magnetic field. Find the magnitude of resultant magnetic field at a point 2 centimeter away from the wire. So this is, if this is a current carrying conductor, there is already an external magnetic field. We will call that as B1, which is equal to 4 into 10 to the power of minus 4 Tesla, which is flowing parallel to the current carrying conductor. But 2 centimeter away from the wire, there is a magnetic field produced by this current carrying conductor, which is given by V is equal to mu naught I divided by 2 pi into R. Let's call that V2, which is 4 pi into 10 to the power of minus 4 into 30 ampere divided by 2 pi into 2 into 10 to the power of minus 2. So you get this magnetic field on calculation as 3 into 10 to the power of minus 4 Tesla. Since B1 and B2 are perpendicular to each other, the resultant magnetic field will be root of B1 square plus B2 square, which will be equal to 5 into 10 to the power of minus 4 Tesla. A long wire having a semicircular loop of radius r carries a current I as shown. Find the magnetic field due to the entire wire at the point O. So here first let's find the magnetic field due to the linear portion of the wire. So due to the linear portion of the wire, the angle which PQ or ST makes will be either theta or pi. Therefore, the magnetic field, which is equal to mu naught by 4 pi I dl sine theta divided by r square. So theta is either 0 or pi. This turns out to be 0. Now let's find it due to this semicircular portion. So due to the semicircular portion, magnetic field dB is mu naught by 4 pi into IDL sine pi by 2 divided by r square, because for at every point for any for a portion of the current element, r is always perpendicular to dl. Therefore, the total magnetic field will be the integral of mu naught by 4 pi IDL divided by r square, and integral dl here is equal to pi into r because that's a semicircle. So that results in magnetic field at the point O as equal to mu naught I divided by 4r. Thanks for watching. For quick revision and solving questions, visit us at Learn from Sita.